Throughout our studies, we've been exposed to a bunch of different theories which all try to make sense of the weirdness that is quantum mechanics. In fact, we've learnt so many that all of their definitions are starting to get jumbled up in my head. What is a wave function? Does it collapse? What is measurement? In this video, I'll attempt to explain the differences between the three main interpretations that we've learnt, starting with the Copenhagen interpretation. This is the one that basically started this whole mess, and it's the one that we most commonly use. It describes quantum systems using wave functions, which contain everything, and evolve according to the Schrödinger equation. This accounts for superposition, entanglement, energy quantization, decoherence, tunneling, a lot of things. When we measure the wave function, it randomly collapses into an eigenstate of that measurement, according to its encoded probabilities. This is inherently probabilistic and non-deterministic. Take Schrödinger's cat, for example. Say there's a cat in a box with a radioactive atom, and the cat's life depends on whether or not this atom randomly decays or not. There are two possible outcomes. You either open the box and the cat is dead, or you open the box and the cat is alive. But before you open the box, you don't know which it is, dead or alive. It is in a superposition of these states, and it only collapses into one of them when you open the box and observe the cat. This is really weird, and this is what made Einstein and Schrödinger so uncomfortable. It says that reality comes from observations, not from the system itself. But how does wave function collapse actually occur? And what even is a measurement? This is called the measurement problem, and it's one of the main faults of the Copenhagen interpretation. It never actually defines what a measurement or collapse is. Einstein was very uncomfortable with the non-locality of the Copenhagen wave function interpretation. It means that information can be communicated faster than the speed of light. As the father of relativity, this was bad. He explored this idea using the EPR paradox, where the measurement of one particle instantaneously collapses the wave function of another entangled partner. This paradox suggests that there's something that we're not seeing, that quantum mechanics is actually incomplete. This led to the hidden variable interpretation, which says that all of our quantum theory is actually just a cute way of statistically describing our system, but our system was never actually in a superposition to begin with. Instead, there's some other grander theory which holds all the answers to our questions. This is deterministic. The particles always had some predefined answers to our measurements, and measuring the state actually does nothing to the state itself. No wave function collapse, no problem. This is also usually local. Measurement of one particle tells you about the state of its entangled partner because it was always in that state anyway. There was no need for communication to be exchanged. Then Bell's theorem came along and showed that local theories could not explain our experimental observations, so any quantum theory must be non-local. Thus, hidden variable interpretation was laid to rest. But there's another way to avoid wave function collapse, and it's gonna sound like some shit from Hollywood, but hear me out. Let's say that for any measurement you make, all possibilities do occur. This is called the many worlds interpretation. So I keep saying worlds in this section, but what I really mean is states. So every time you measure the particle, you become entangled with the state that it's in. So now there exists a superposition of Sarah who measured spin up and Sarah who measured spin down. So your entire world is just one big entangled superposition mess. By definition, it predicts all experimental outcomes and is completely deterministic. It even says that the universe is described by one giant wave function which contains everything that ever was and ever will be. This should make you uncomfortable, since it kills any philosophical notion of free will or absolute identity. Your fate has been predetermined by a wave. One cool thing that comes from this is the concept of quantum immortality. Imagine a Schrödinger's cat situation, except that now you are the cat, and the measurement is performed by you eating a poisoned quantum M&M. Just bear with me. A normal person would say that every time you eat an M&M, you collapse the wave function and find out if you live or die. This probability adds up. After 2 M&Ms, there's a 25% chance you're alive. After 3, 12.5. After 4, holy shit, stop eating the M&Ms. In the many worlds interpretation, you will live. This is because every time you eat an M&M, the timeline splits off into 2, dead and alive. No matter how many semi-poisoned M&Ms you eat, there is always one timeline where you will end up alive. Your consciousness splits off at every M&M, and since you can't actually experience being dead, who cares? Yes, now there are a bunch of worlds where you tragically died, but there's also an 100% chance that you lived. So there you go, those are the three interpretations that we've learnt so far. The Copenhagen interpretation is probabilistic and involves superposition and wave function collapse. The hidden variable interpretation says that particles have some secret labels on them that we don't know about, and the many worlds interpretation says that everything that can happen does happen. Both are deterministic and avoid wave function collapse. There are so many more interpretations out there which are even more confusing and world-shattering, and which make you really question everything that you know about life itself. But it's okay, because those aren't on the exam.